Hello, everyone. I'm Johannes Hefter, and I will show you today which common database challenges in StableNet you might be able to solve using TimescaleDB. I will start off with a really short overview what TimescaleDB actually is. We talked about this previously, so maybe also just a quick refresh topic. So basically, TimescaleDB is an add-on or an extension for Postgres. So Postgres already is a fully featured database, and TimescaleDB is basically built on top of it, providing time series functionality. And this combination is already providing everything we need for also the main StableNet database. Yeah, funnily enough, we already supported Postgres a while ago, or more or less a longer time ago. But at some point, competitors like MariaDB were introducing partitioning. And since we wanted to rely on that back then, we dropped support for Postgres and moved over to MariaDB. But with the introduction of TimescaleDB, a time series extension for Postgres, we want to also support Postgres again in the future. So we plan to officially support it with StableNet 27 as a main database again. Technically, it is already working right now with StableNet 26. We simply do not want to offer official support for it yet because we want to do some further testing and different testing setups at InfoSim. But we also want to encourage you, if you want to try it out for yourselves, you can contact us, contact our support team, and then we can set it up for your testing system. So you can also check out if this new database setup would work for you. I go into a quick comparison between what we did so far and what this Postgres and timescale setup does differently. And then I will show you some examples and some statistics we got from our test systems where we already deployed the setup, and we'll have a look how well it works. Yeah, so the traditional setup we do as of now is we have aggregation tasks that handle measurement aggregation, and we have one table per measurement type. For example, the SN-ping data or the SNMP data are two tables that are used heavily. And those aggregation tasks basically aggregate the data depending on how old the data is, but stores all of it into the same table. This had a nice advantage that you can simply, for any plot, you can query this one table and you get all of the data out of it. But it also brought several disadvantages. One thing is the aggregation task itself, the maintenance in our case, it causes lots of load on the database and also for a long time. So we have customer systems where it takes several days, if it's a really large system, to finish the maintenance jobs for the database because the aggregation took so long, and then you have the load all of the time until this maintenance is finished. And also, a second point is that when you have really long plots or plots at the edge of where one aggregation interval ends and the other one starts, this was really visible in charts because you don't then have like more data points in the more present part of your plot and less data points in the past. And also the statistics were incorrect. For example, quantile calculation was sometimes an issue if you are exactly working with different intervals in one plot. Yeah, the continuous aggregation format does take another approach. So we have we take the views the time series database offers us. And this means we have not only this SN-ping data table, for example, in the database, but we also have hourly and daily aggregates that come along with it and that are managed by the database. This, of course, brings also a disadvantage, because when we now want to query data, then we have to select the correct table for querying it. It's because there are 3 of them now. But we have some functionality in place to mitigate this issue a bit, and this is what I will show to you later live. And on the other hand, we have lots of advantages coming with it. Since the time series database is able to do the aggregation itself, this will just happen in the background automatically. So no more long aggregation jobs running during maintenance. Also, when we do this query, after we selected the correct table, we have already the aggregation level set. So this is also really great. We have then one aggregation level for the whole chart, and we don't have any statistical inconsistencies anymore in there, or some issues with more or less data points, depending on the time. What comes on top, what was not previously possible, is that you can then define data retention individually, depending on the aggregation level. Meaning you have not only the daily aggregates for data that is older than a year, but you have daily aggregates starting yesterday until a defined time in the past, where you can say, okay, keep this daily aggregates for 5 years, hourly for 1 year, and raw for 3 months or something, and then you have all of those different views ready all of the time. Also, old data is dropped automatically by the database, so also no need for our maintenance job to handle this. And also, what is really nice is that especially for the measurement data tables, we save around 90% of disk space when we use the compression features of TimescaleDB. And this is also where I wanted to jump in to the live demo, just about because of the compression, because we introduced not only like the database support, but also we extended our database manager. So the database manager has now some additional commands where you can see how the compression is performing when you have TimescaleDB running. So there is this compress info command now for the database manager. This is some of our test system that has lots of simulated devices on it. So lots of SNMP data that is actually generated. And what you can see right here is then an overview you get from the database with each table listed here. And for example, the SNMP data table is interesting lots of most of the time, or the ping data one, at least for our testing setup, because we have lots of SNMP data. And what you can see is, of course, the table name, the aggregation configured. So this is the raw data table. And then we have the uncompressed disk space it would take, the compressed space, if everything would be compressed, it would take, and then the total space it actually takes. Because we do not compress everything. I will also come to this one a bit later. And yeah, but this is what you can see right here. You can also see that we have the daily and the hourly views. They are also listed here. And those are also compressed. So yeah, as you can see right here, it does not perform as well with the hourly as with the raw data, but still something. Yeah. What you can do on top now with this manager, when you have the timescale set up in place, you can also get detailed compression infos on each table. So with this compress part info, for example, you can load the compression information on one table. And here you also can see a bit how the database works internally. So there is like one chunk per day, And you can see all of those chunks are compressed. So each day was like 42 gigabytes of SNMP data, raw data, and we have 500 megabytes in total space. Because this one was compressed, the only chunks that are not compressed are the most recent ones, because it is more performant to write into uncompressed chunks, and because the agent may also be like not available for a day or two, there is a few days that we are keeping uncompressed in order to improve the write performance. Yeah, but all of the other chunks are compressed, and the compression only happens inside one chunk, as you can see. Same would now be possible if you wanted to for the aggregates. As you can see right here, not so many because the chunks get larger. It's 10 days. And as I said, compression is not as efficient because, yeah, we have less data points in one chunk compared to the raw data that has intervals of 1 minute or 5 minutes maybe. And yeah, also you have more averages in there. And so on. But this is like the rough idea that you can get how you can actually analyze your setup if you have TimescaleDB in place. Now, a second thing that is interesting when you have this in place is, as I said previously, the challenge when you have multiple views and you need to query one of them for data. Meaning, if you create a chart in here and you have an analyzer, and then as you can see, there is a data source that is selected or not selected. And in this case, the internal one is selected. It's a default. You can also see it up here. So we use the internal one. But there is also the daily and the hourly aggregates in our internal database. And what we now implemented is a query optimizer that takes the correct data source based on your query. Meaning if you, for example, switch to the 30 days of data in here, then you can see we automatically switch the data source for you and query the hourly aggregates, because also the average period matches better. It's that is then selected with the 30 days query. And yeah, and this has the goal to, on the one hand, reduce the processing needed on the server side, and also reduce the data transferred between the server and the database, because the database is doing the aggregation for us and the server is just using the data as it comes and more or less displays it. And this also works not only if you select the correct data source, but also on the fly in some scenarios. Yeah, but you don't have to rely on this optimizer if you don't want to. You could still select the internal one or select the daily one. But yeah, my system is not running for so long and it's a developer system, so this runs only during day. So this might be not the best aggregate to show. But yeah, that's basically it. Showing you why we selected TimescaleDB additionally, how you can test it, how you can see in your own setups if it works and how good it performs, and also the measures we took to somehow mitigate the disadvantage of the query selection with the TimescaleDB. Thanks for your attention.